Today we're going to be working on 3 polynomial functions and their graph. Remember, a polynomial function is a function in that form where the degree is n, and remember, back from 3-1, when we talk about degree, that is your highest exponent. And the graph is smooth and continuous. In other words, I could draw the graph without lifting my pencil again. So let's take a look at a couple examples here. I have 2 polynomial functions. If I want to know the degree, I am looking for the highest exponent. In the case of the first one, it is already written in standard form, which means it goes from your highest exponent down to your lowest. So my highest exponent is 4, therefore this is a 4th degree polynomial. If I look at the second one, this one is not written in standard form and would be one that I would require you to rewrite in standard form. And so I'm looking for my highest exponent. It is 3, so this is a 3rd degree polynomial. Today we're going to talk about end behavior. End behavior is a description of the y values as x becomes large in both a positive and negative direction. End behavior is this entire statement right here. So if I'm asking you to write end behavior, you need to write that whole statement. So we have a notation as x goes to negative infinity. That's what the little arrow means, goes to. Y is going to go to something. It's either going to be a number or the infinity sign. And what that means is, what is y doing on the left side? Okay, and then the other half of the end behavior notation is as x goes to infinity, y goes to, and I'm not sure, again, that'll either be a number or the infinity sign. And what we ask ourselves is, what is y doing on the right side? So from here, we're going to take a second and look at the graph's pictures. That is how we are going to determine end behavior, is from the pictures of the graphs themselves. So if I look at example 1, I have 2 different types of polynomials. And we classify polynomials by their degree. And when I look at their degree, which are numbers, they can either be odd or even. So odd behavior or odd degree functions, and this is not saying the function itself is odd, but odd degree functions have a different end behavior than the even degree. In other words, for my odd degree, I have exponents of 3, 5, 7, 9, something like that. Even degree has my highest exponent is 2, 4, 6, 8. So looking at odd degree functions, if I am looking at this part, so as x goes to negative infinity, this is what I'm looking at, just a little snapshot of that part of the graph. In other words, if I didn't know what else the graph was doing, what is it doing in that particular moment? So as x goes to negative infinity, y is going down. Therefore, y is going to negative infinity. Now if I look at the right side of the graph, so as x goes to infinity, I'm going to look at this little snapshot here. What is the end of the graph telling me it's doing? It is going up, which is a positive infinity. Here I have x goes to negative infinity, so that's the left side of the graph. What is that telling me? It's telling me y is going to infinity. And now if I look at x goes to infinity, what is the right side of the graph doing? It's going down, so y is going to negative infinity. So what can I conclude about their behaviors? For odd degree function, you will notice they always go in the opposite direction. So in other words, as one side of the graph goes up, the other one goes down. That will always happen with odd degree functions. So if I come over here and I look at the even degree function, so as x goes to negative infinity, what's it doing right here? So as x goes to negative infinity, y is going to infinity. It's going up. Then if I look at the right side of the graph, as x goes to infinity, y is going to infinity as well. Over here, the left side, as x goes to negative infinity, y is going down, so that's negative infinity. And as x goes to infinity, y is going down, so that's negative infinity. So what can we conclude about their end behaviors? They always go in the same direction. So for odd degree function, one's going to be up, one's going to be down. Even, they're both up or both down. So next we're going to talk about zeros of a function. So the zeros of a polynomial function is the point on the graph where it crosses the x-axis. This is also known as a root or an x-intercept. So anytime I ask you for a solution, a zero, a root, an x-intercept, it's all asking for the same thing. Where does it cross the x-axis? If a polynomial is a zero, or if c is a zero of a polynomial function p of x, then the following is true. X equals c is a root that makes p of x 0. And x minus c is a factor of p of x. Remember, my degree of the polynomial always equals the total number of zeros. In other words, if I know it is a fourth degree polynomial, that polynomial should have 4 zeros. Now, this doesn't mean that they are all real numbers. It could have some imaginary zeros, and we are going to get into that later on in this unit. But today we are just going to focus on real when I'm looking at the graphs. So the next thing is something new. We haven't talked about it before. It's multiplicity. So a root of p of x has a multiplicity of 1 if it just crosses the x-axis. In other words, it just crosses the line and keeps on going in the original direction it was going. That is a multiplicity of 1. That's what we're used to seeing, where it just goes straight through the graph and keeps on going. A root has a multiplicity of 2, and you can shorten that as MO2, if its root touches and then turns around at the x-axis. So if I think of it like a ball against a wall, I hit the x-axis and it turns back around. That means I have 2 zeros at that point and not just 1. That's what makes it turn back around. So let's look at our chart. So we need to be able to go between 0 and factor in this unit, and we need to do it very seamlessly. So we're going to review some things. So if I have a 0 at 3, that means I have a factor of x minus 3. Okay. So if I have x equals 3 here, and I want to make it a factor, that means I need to set it equal to 0. So I'd subtract 3 from both sides. It's basically going backwards from what we've done in the past. So a 0 at -1 would be x plus 1. It is always the opposite sign. So here, if I look at x equals 1/2, first thing I have to do is divide or multiply both sides by 2. So I have 2x equals 1. Now I would subtract. And that's my factor. So it's 2x minus 1. In other words, it's still the opposite sign and then the numerator, but my denominator becomes my coefficient of x. So for -2/3, that's going to be 3x plus 2. 3/4 is going to be 4x minus 3. And this is the one people forget. If I have a 0 at 0, that means I have a point. That means I have a factor, and the factor is simply just x. So if I look at my graph, let's take some of these things that we just talked about and put it into play. So we're going to start here, this one. That as a 0 is just 1. Okay. So as a factor, that would be x minus 1. Okay, it just hits the x-axis and keeps on going. So that has a multiplicity of 1. We don't need to mention that anywhere. It is understood to be 1 if we don't say it. Here, you'll notice it touches the x-axis but then does a U-turn. So for a 0, it's at -2, but I'm going to say it has an MO2. In other words, it happens twice there. As a factor, that would be x plus 2, and to make it have a multiplicity of 2, I simply put a squared up. In other words, it has 2 factors at x plus 2. So if I look at example 2, it says find the zeros and the factor of each polynomial. We're going to use our calculator or Desmos to help us out. So let me switch over to Desmos and I will show you how to go about finding these. So first thing I'm going to do in Desmos is type in my function. It was y equals 3x squared minus x minus 2. And the great thing about Desmos is it puts my points down there. So if I hover over it, it will tell me what my 0 is. Now, you need to know your fractions. So I know this fraction, a negative 0.666667, is negative 2/3. So if you don't know those, you do need to be able to figure them out. And then I have a 0 at 1. So I'm going to switch back over and we are going to put that information in. But this is how you are going to get your zeros of your polynomial right from the graph. So since this had a degree of 2, I knew there were going to be 2 zeros. And we just found them. It was negative 2/3 and 1. So negative 2/3 as a factor, remember our denominator becomes our coefficient. I change the sign, put the numerator. And 1 is simply x minus 1. If I look at b, my highest exponent is 3. Therefore, I know this is going to have 3 zeros. Again, I would just go over to Desmos and type it in. When I do, I get negative 3, negative 1/4, and 2. So negative 3 as a factor is x plus 3. Negative 1/4 as a factor is 4x plus 1. And 2 as a factor is x minus 2. Last one to look at is the C. This has 4 zeros. So when I look at my graph, you'll notice that I have negative 4, but it hits it twice. I have an MO2. So that really takes care of 2 of my zeros. I have a 0 at 0 and a 0 at 5/2. So as a polynomial then, this would be x plus 4 squared times x times 2x minus 5. So the other part of today, in example 3, is now I'm going to give you the polynomial, or the zeros, and you have to give me the polynomial. So the first thing I need to do is write these as factors. So it's going to be p of x equals negative 2 would be an x plus 2, and it happens twice, so it's squared. 4 is x minus 4. Now we're going to have to multiply it out. So whenever I multiply, I always multiply two things together. You can't multiply more than that in a polynomial at a time. So I'm going to go ahead and take care of this squared first. So from our shortcut method, it's square the first, multiply and double, square the last. And I'm going to bring down the x minus 4. From here, I'm going to go ahead and distribute the x squared to both terms, the 4x to both terms, and the 4 to both terms. So I will get x cubed minus 4x squared. Okay, now I'm going to move, that was the x squared term to both. Now I'm going to move on to the 4x by both. So that becomes 4x squared minus 16x. And now we move on to the 4. Okay, this is what I'm doing. So that gets me a 4x minus 16. Now I simply combine my like terms and I'll get x cubed minus 12x, because my x squareds cancel out, minus 16. And that is what p of x is. Okay, on to B. So again, first things first, I'm going to write it as factors. So it's x plus 3. It is 2x plus 1. And it is 4x minus 3 twice. So I'm going to multiply these two together. So we're going to FOIL it out in combined like terms. When I do, I get 2x squared. And my outsides and insides added together is 7x. If you need to write out that step separately, you may. And my last is 3. Those stay in parentheses. But I also have a pair here, so I'm going to go ahead and FOIL that out too to save me a step. So it's 16x squared minus 24x plus 9. From here, you could go ahead and distribute the same way we did on A, or you can use the area model. Sometimes I find it is easier to do that over to the side, so I know for sure I don't miss anything. So I'm going to do that over to the side and show you what that looks like. So if you can remember, the area model is where we draw a box and we put one polynomial up on top. So that's the 2x squared, 7x, and 3. And I put one polynomial down the side. So 16x squared, negative 24x, and 9. And now what I need to do is fill in each box. So to get the answer to this first box, I multiply the sides of the box. And we get 32x to the 4th. And I continue that along. So 16x squared plus 7x is 112x cubed. Then I have 48x squared. And I have a negative 48x to the 3rd. Negative 168x squared. And negative 72x. 18x squared. 63x. And 27. The other thing I like about the box method is all of my diagonals hold my like terms. So I have an easy way to see what I need to combine. So my final answer for this polynomial is P of x equals 32x to the 4th plus 64x to the 3rd minus 102x squared minus 9x plus 27. Feel free when multiplying your polynomials to do it the way that works best for you. If you prefer the box method, do it. If you prefer just distributing, do that. But make sure you don't miss any terms and you are always multiplying out what needs to go together. So the last thing that we need to talk about is our local extrema. These, remember, are critical points. They're the points where the graphs turn around. These are our minimum and our maximum points. We need this information to be able to help us draw our graph, because these are points that you need to plot. I don't ask for much when I ask for you to plot your graphs or draw your graphs, but I do ask that they are exact as can be. So you have to plot your zeros, your maximum points, your minimum points, your y-intercepts. Those are must-haves for graphing any polynomial as exactly as we can. So a polynomial p of x with a degree of n has at most n minus 1 local extrema. Please put a star or highlight or a note by this concept. This is always on my test for this unit, where if I give you, let's say, a 5th degree function and ask you how many local extrema can it have, you would say 4. It's always 1 less than the degree. Does that mean it has to have 4? No. But at most, it can have 4. So now if we look at example 4, and I'll move it down just a second, but it says complete all blank information about the polynomial p of x. If I look and I don't know what this maximum point is from looking at my graph. So we're going to use Desmos again to help us figure all this out. So that's where we're going to go next. Let's go plug this into our calculator or Desmos, whichever you would prefer. So I'm over here at Desmos, so I'm going to plug in my polynomial. Y equals negative x raised to the third plus x squared plus 5x plus 3. Now as you can see, I can't see all the points I need, so I'm going to zoom out until I can see them. Now you'll notice all of my important points that I need for my sheet are on here. I have my x-intercepts or my zeros. I have my y-intercept. I have my maximum. And you're only going to have to write it down to 1 decimal place because we're graphing by hand. And I have my other 0. So this is why it's so important that you use Desmos. It makes this stuff a lot easier. If you're using your calculator, you're going to have to use the calculate function to find your maximums in zeros. It doesn't just give it all to you. So let's take this information and go back to our graph. So from Desmos, we learned that I had a 0 at -1. And that had a multiplicity of 2, so I'm going to make sure I put that down. And I also had a 0 at 3. So as factors, that -1 becomes x plus 1 squared. And that 3 is x minus 3. So we've also just factored our polynomial just by using this information. I had an extrema, I had a minimum at -1, 0. Yes, it was also a 0, but it still is a minimum. It's a valley. It's a dip in the graph. And I also had a maximum at 1.7 and 9.5. My y-intercept was the 0.03. And my end behavior, as x goes to -infinity, y goes to infinity. And as x goes to infinity, y goes to -infinity. Now we would go ahead and do that for both of these next ones. I am going to just write down the information because I already have it from Desmos, but that is where I'm getting it from. So if I look at this next one, I have zeros at -4, 0, and 2. And you may have to zoom out and zoom in when you're using Desmos. That is understandable. So my factors are x plus 4, x, and x minus 2. So I'm going to go ahead and plot those. So I had a 0 at -4, I had a 0 at 0, and I had a 0 at 2. My extrema, I had a minimum at 1.1 and -5.1. I had a maximum at -2.4 and 16.9. So I'm going to plot those as well. And those are just going to be estimates since it is, since they are decimals, we just try to get as close to it as where we would think it would be. 1.1 and -5.1, somewhere around there. And -2.4 and 16.9. Okay. So when you're graphing them, please make sure I can see these points. I need to be able to see them. I also had a y-intercept of 0, 0. That's already plotted in my graph because I already plotted my 0 of 0. From here, we just connect our points. You don't need to add any extra points. You just need to connect those important key points, and we call it good. So my end behavior is x goes to negative infinity, y goes to negative infinity. And as x goes to infinity, y goes to infinity. Last one for this part. C, I have a 0 at negative 3/2. I have a 0 at 2, but that happens twice. And I have a 0 at 4. So my factors then would be 2x plus 3, x minus 2 squared, and x minus 4. So I'm going to go ahead and plot those. So negative 3/2 is negative 1.5. 2 and 4. Okay, my extrema, in this case, I have two minimums. I need to write them both down. I have a negative 0.5 and negative 56.3. And I have 3.4 and negative 11.5. I also have a maximum of 2, 0. So 2 zeros are already plotted, so we're going to do negative 0.5 and negative 56.3. And 3.4 and negative 11.5. I have a y-intercept of 0, negative 48. And again, now I'm just going to go ahead and connect my points. And I know 2 had a multiplicity of 2, so it just touches the line and comes back down. And there's my graph. So the end behavior is x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to negative infinity. We just have one more problem we're going to do. We're going to do a word problem, and that is it for this lesson. So if I look at example 5, it says a metal worker wants to cut an 8-inch by 6-inch sheet of metal. So I'm going to draw this out. So my picture is going to be just a brief or a quick picture. It's not necessarily to scale. So this is 6-inch by 8-inch. Okay. And we're going to take that and transform it into an open top box by cutting equal squares in each corner. In other words, in order to make this sheet of metal fold up into, think of it like just a bottom box, I have to cut out some corners so I can fold it and things match up. Well, I don't know how big those corners are that I'm cutting out, so we're going to put an X there. Now, because of that, this new length now for my box would really be 8 minus 2x. And this new length for my box is going to be 6 minus 2x. And the height of my box is simply x, because that's what I'm folding it up at. So what is the maximum volume for this box? So remember, volume equals length times width times height. So I'm going to put that in there. My length would then be 8 minus 2x. My width is my 6 minus 2x. And my height of my box is x. Now the great thing about Desmos, and we're going to switch back to it in just a second, is that I don't need to multiply this out. The calculator will still calculate my volume without me having to FOIL this whole thing out. So let's switch over so I can show you what I mean. So I'm going to go ahead and type in here what I just had on the other slide. I'm going to have 8 minus 2x times 6 minus 2x times x. And if I want to maximize volume, I need to find my maximum point. And this is where it happens. Happens at 1.1 and 24.3 if I round off. So let's go back to our other slide and I'll show you how we write that down. So back here, what is the maximum volume of the box? So we just said my maximum point was at 1.1 and 24.3. That was my maximum. This is where it happens. This is my volume. So my maximum volume is 24.3 cubic inches. Now, what are the dimensions of that box? So we're going to plug 1.1 in. So my height is just 1.1 because that was my x. My width, that's going to be 6 minus 2 times 1.1, which was 3.8 inches. And my length is 8 minus 2 times 1.1, which is 5.8 inches. And there are the 3 dimensions. Okay, that is it for this lesson. If you have any questions, please feel free to email me, and I will be back tomorrow.